Have all these people listening in. The title here is Beyond Anthropic Fine-Tuning, the Fine-Tuning for Discovery. It's not that I reject any of the anthropic fine-tuning. I just think there's a powerful addition to it, the fine-tuning for discovery. And I'm assuming people are familiar with the anthropic fine-tuning argument in my audience. So let's look at the motivation for this. It's already been noticed by physicists and many other philosophers that the fundamental order of nature is much more discoverable. Sometimes it goes under intelligibility than would be expected by, quote, chance as a brute fact. So here you have examples of well-known physicists. Albert Einstein, for example, has been famously quoted as saying the most incomprehensible thing about the world is that it is comprehensible. Eugene Wigner, the miracle, the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. And now here's a quotation about the relevance of some of this to one of the major objections to the anthropic fine-tuning, the multiverse hypothesis. So it is perfectly possible for there to exist a universe that permits the existence of observers who nevertheless do not or cannot make much sense of nature. In fact, the physics of our universe is extremely special, being both simple and comprehensible to the human mind. This understandability factor is left out of anthropic and multiverse explanations. Oops. So the discoverability provides a test for the multiverse. Basically, the puzzle is, why do we exist in a highly discoverable universe? So here's us in a highly discoverable universe. Here's all these other universes that observers can arise in, but they're sad wannabe physicists in those universes because they're not highly discoverable. So in a probabilistic analysis, assuming for now an equal probability distribution, and assuming that there's only a very small proportion of observer-permitting universes are highly discoverable, and one does not know if one is in a highly discoverable universe or not, like a 19th century physicist, for instance, then the epistemic probability or subjective probability here of our universe is highly discoverable under a many-universes hypothesis, or just without many universes, would equal the proportion of universes that are highly discoverable, which would be much, much less than one. So a very small probability. In contrast, this is the old evidence problem for the anthropic fine-tuning. Our universe is observer-permitting under many universes equals 1, as it does without many universes. Oh, that should be with no many universes there, typo. So here was my idea, and I really stumbled across this in 2010. So I've mostly been doing physics and cosmology since 2010, when I was working on the anthropic fine-tuning argument, trying to solidify the physical arguments for it. And so this idea came about. Can we quantify and test discoverability? And I think the answer is yes for this. We can look at our ability to discover the universe when we vary the values of the fundamental parameters of physics, like the ones in the standard model of particle physics or the cosmic parameters, and a limited number of those. So that's what I began doing, looking at what happens when we vary those parameters. And I came up with two major theses to test. One is a simple discoverability fine-tuning thesis, is that, if we move this around, among the alternative universes generated by varying the fundamental parameters of physics, a very small proportion are as highly discoverable as ours. So most of the parameter space, it's much less discoverable. And then the strongest of the theses is this, as I call it the discoverability livability optimality thesis. And this says within the livability optimality range, the actual value of the parameter given by the star here will fall into what I call the discoverability optimality subrange. Okay, and I didn't initially have that thesis, but the data seemed to indicate that was the case. So I want to test even that stronger thesis, and it's actually turned out to, in all cases, there's no counterexamples, even though I thought there were about 7 times, but then I found mistakes in my calculations or something like that. So let me give you next what I'm not claiming. I'm not claiming we live in the most discoverable universe. Only that we live in the most discoverable among those generated by varying the fundamental parameters and within that livability optimality range. And why the limited claim? Because I think if you're a theist, elegance and interestingness are tied to the underlying mathematical structure. So you want to keep that the same. I'm only varying the constants, not the mathematical structure. And God might have good reason for also trying to optimize these features. So I'm really going to test discoverability. I want those to stay constant. So these are tied in with the mathematical structure here. And just as the start, I'll say most of my calculations have been checked over by at least 3 physicists, except for the particle physics cases, which ones were actually the strongest cases, which I hit this summer, and it's only one physicist I've had time to check them over with. So this is the first example. This is the one I first stumbled across in 2010. And that is the fine-structure constant, usually designated by alpha. It's a physical constant that governs the strength of the electromagnetic force. If alpha is larger.
Do you want to try this, Robin, or do you want to try to stay close to your
I can stay close. I'd have to hold
Yeah.
that another. Is it okay to sound? Okay.
Close. When you turn all the way around, it's hard to hear.
Maybe I grab that.
Or just stand maybe off to the side.
Okay, off to the side here. Okay.
There you go.
So if you increase alpha, the electromagnetic force is stronger. If you decrease it, it's weaker. Now, this has an effect on fire. If alpha were slightly larger, open wood fires, or that of any other biomass, would have been impossible. Without such fires, it is far less likely that intelligent life forms would learn to forge metals and thus develop a scientific civilization. So this is the only one I'm going to give any kind of detailed rationale for, just so you can see the kind of reasoning that goes behind this. So I came across this by translating everything into atomic units. And in those units, when you change alpha, chemical reactions don't change. Convection doesn't change. But what does change is the amount of radiant energy emitted from a fire or a hot object at a given temperature. It turns out to be proportional to alpha squared. So look at this fire here. If we increased alpha, that would cause an increase in radiant energy emitted, more energy leaving the fire, and since the combustion stays the same, the rate of convection stays the same, that energy has to come from somewhere, so it's going to have to pull energy out of the fire, dropping its temperature. And then you do that, increase it by very much, and alpha can go over a huge range. Increase it by very much, 10 to 40%, your temperature falls below the combustion point and the fire goes out. Interestingly, if you go in the opposite direction, you get another problem. And that is, you can actually see this on the wood surface here. Alpha is already on the borderline of being too large. And so only wood that's facing other wood, where it's getting radiant energy back, can continue burning. If you flip it over, it's still getting oxygen and all this kind of thing. These sides of the wood that are exposed to the exposed side of wood still getting the same amount of oxygen, but they quit burning. And that's a good thing, because if you had a lightning strike, let's say, and they didn't quit burning, then the lightning strike hits a tree, it starts burning, and it won't go out. Typically, they'll just go out because most of the wood's going to be exposed. Okay, so it reduces the number of forest fires and therefore makes wood more accessible. So just within that, there seems to be this problem, forest fire problem. If you move it this way, move it that way, no open biomass fires, and its current value is this right here. It's the upshot. There's also a lot of other effects if you change around alpha, particularly if you decrease it. As soon as you decrease it, you decrease the maximum resolving power of light microscopes, which are necessary to see living cells. You can't see living cells with electron microscopes. Interestingly, the maximum resolving power is 0.2 microns, and the smallest living cell is 0.2 microns. So interesting coincidence there. You also, very quickly, the efficiency of transformers and motors rapidly drops off with an increase in alpha. It's so fast that a very moderate increase, maybe twofold to threefold decrease, you wouldn't probably even be able to use them anymore. So here are some of the discoverability constraints on alpha. So those are some of the very early cases I found. The next one was, for a long time, the most impressive case I had, and that's the cosmic microwave background radiation, the radiation that permeates the universe from the leftovers from the Big Bang. This radiation, after starting from the Big Bang, has redshifted, so it was very short wavelength initially, like in blue wavelength, and then it's redshifted to the microwave region, and right now, which is much longer wavelengths. That's why it's microwave radiation. And the CMB is a key tool of cosmology. It's often called the Rosetta Stone of cosmology, because it carries information about the overall structure of the universe. So here is my reasoning that the CMB is already fairly weak. The information is encoded in very slight variations in its intensity of sometimes they're looking at 1 part in 10 million, the Planck Explorer satellite, of its intensity to gain information to test cosmic theories. So within limits, the more intense the CMB is, we can then measure smaller variations, and the more useful it is for cosmology. So you would expect it to, within those limits, to be maximized. So the CMB depends on what's called the baryon to photon ratio, which is just the number of protons and plus neutrons over photons in the universe. And a prediction of the DLO, the discoverability, livability, optimality thesis, is that if the universe is discovery optimal, we would expect the value of this ratio in our universe to maximize the intensity of the CMB, given there is no other factors. So I first did a calculation for this in 2011. It's actually a fairly difficult calculation. And I made a mistake. No one had done it before, so I did it. Made a mistake, and I thought I refuted my thesis. So I came back to it in January 2012, realizing I'd made a mistake, corrected for the mistake, and this is the result I got here. This is over a factor of 1 billion-fold from 0 to 1 billion. And here's the curve. This is our photon baryon ratios right there. I'm looking at alternate universes with different photon to baryon or baryon to photon ratios. There's where we're at. This is the intensity of the CMB. Notice where we're at. That's supposed to be a smiley face. We're right there, right at the peak. That's where we're at. This is a very impressive result. I didn't initially think I would get this. I was kind of shocked. So I sent it off to 4 different people, including one person at Baylor University, who's the string cosmologist here, Gerald Cleaver, and they all end up agreeing with me. In the end, they agreed my calculations were correct. So that was the first really major result I got. That was really kind of stunning. So it wasn't until actually this summer I finally did the particle physics cases, and there now I think I got the best result. I always wanted something as impressive as the CMB, because I think, if you win the lottery once, you can kind of ascribe it to chance, but if you win it twice, okay, then you should get suspicious, okay? So I started looking at these cases, and actually it's because of an objection Sean Carroll raised to me last February. in the Greer-Hurd form, coming from particle physics cases, that I started looking at them. So I didn't know what I was going to find. I thought, well, maybe, they would refute my thesis. And I was very pleasantly surprised, or sort of surprised, because I was suspecting this thesis was true. So let me go through, first of all, what fundamental particles are. I'm not assuming people have much knowledge of physics, and this is for a more general audience. So, we normally think of, let's say, atoms are composed of, is there a problem with this still?
I'm just getting it as close to you as I can.
Okay, we normally think of, or ordinary matter is composed of atoms, which are composed of electrons and protons and neutrons. The protons and neutrons are further thought to be composed of quarks. This is a down to up quarks for the proton. And so the fundamental particles in ordinary matter are electron, up quark, and down quark. It's 3 of them. So those are the most fundamental. They're non-composite. That's what we mean by fundamental. Now, the particles were found to come in generations. That means they have heavier sisters. So here, both the up quark and the down quark have 2 heavier sisters with almost identical properties except for mass. The electron has 2 heavier sisters also. So here you have the charm quark, as an example, circled, is a second generation up-type quark. It has all the other properties of up-type quark. Charge of 2/3 plus 2/3, spin of 1/2, but it has a higher mass. The muon, just like the electron, except higher mass. So there's 3 generations, and then there's these, which are the force carriers, and there's what was recently discovered, the Higgs boson. Now, the standard model of physics, it's the most fundamental theory of matter. This model consists of the particles shown in the last slide, which I show again down here, along with equations governing their interactions. So it's a mathematical theory. And the particles I considered were these, because it's not that the rest of them weren't discovery optimal. It's just much harder to make the case for them. There's no reason to think they're not. So what I looked at is the charm quark, mass of the charm quark, mass of the top quark, and the mass and what they call the CKM matrix element of the bottom quark. And these govern the lifetimes of these particles. And having a sufficiently long but not too long lifetime is actually very critical for particle identification, which is critical for using these particles as tools to probe the standard model. So major elements of the standard model, since the Higgs mechanism, are not well understood. So what physicists are doing in these places like the LHC, Large Hadron Collider in Europe, is they're looking at how these particles decay and their behavior to try to more thoroughly understand the standard model of particle physics and test its limits, whether there's a new physics lying beyond it. Okay? So that's like the main thing that's being done. And one other thing is probing what's called CP violation, charge conjugation imparity, which is essential for the fact that our universe has mass and is not just pure energy. So that's the goal. So I mentioned the identification of these particles critically depends on their lifetime. And the particles seem to have an ideal lifetime for such identification. And this, in turn, depends on the fine-tuning of several parameters. So here is the case of the bottom quark as an example. And here's physicist Matt Strassler. He was at Harvard. Bottom quarks, he says, have lifetimes in a sweet spot. The distance that bottom quarks typically can travel before they decay turns out to be an ideal distance for detection by the LHC detectors ATLAS and CMS, and the Tevatron detectors CDF and D0, and many other experiments too. And why is this the case? They initially thought they weren't going to be able to do much with the bottom quark when they initially discovered it, because it has a high mass and the lifetimes are inversely proportional to the 5th power of mass. They thought it was going to be way too short lifetime to be able to study CP violation and other things, but they were pleasantly surprised to find that this is what matrix elements, part of the Km matrix. And if you move it in this direction, this element here, the lifetime increases. It gets longer and longer as it approaches 1. Okay? Increases very rapidly. So it was anomalously large. It can be between 0 and 1, and its actual value is 0.99995. And it requires that, so the calculations to be between 0.997 and a little larger than that is where you're going to get the ideal. So it's this little strip here, and that requires a fine-tuning of about 1 in 300. That was one of the cases, and then I looked at the mass of the charm quark and the tau lepton. Well, I said if it's the inverse power of the 5th power of their mass determines their lifetime. So if you move them up here, suddenly the lifetimes become far too short for them to be identifiable. And there's a reason for that. If I have time, I'll say what it is. You can ask me in the question and answer session if you want. And likewise here. And if you go too low, there's another problem that arises. So there's a little strip here. And before the Higgs field goes unstable, each of these can go up to about 150 GeV. It's a way of measuring mass. And then the Higgs field goes unstable and there's no life. Okay? Higgs field right now is in a metastable state, actually, which is also good for discovery for another reason. Then, and this is the one Cheryl challenged me on, was the Higgs boson. So that's when I started getting interested in the standard model. I kind of had stayed away from it because I thought it was going to be too complicated. And they discovered the Higgs boson to be a mass of 125 GeV. And after the discovery, this was one of the major physicists that worked on it. He wrote this like 400 and like 10 years earlier, all about the Higgs boson and how it would be, detection schemes and what it would be used for. And then after it was discovered, this is what he said. He said, the Higgs particle was born under a very lucky star. The mass value of this allows us to produce the Higgs particle at the LHC in many redundant channels and detect in a large variety of decay modes, which is important for discovery. And then another particle physicist says it's an ideal scenario for studying its couplings to other particles. And that's the key thing they use it for, to probe the standard model. So if you put them all together in the case of the standard model, forgetting those other cases I talked about, you get, I think, a reasonable estimate is 1 part in 112 million of the entire parameter space you're dealing with. There's a really small area that's where you maximize the particle identifiability and those other features that seem key for discovery. And then if you want to be more conservative, it goes down to by a factor of about 100 to 1 in a million. So it's an addition to all the other cases of fine-tuning. So I think you get what I call the discoverability, livability, optimality thesis before, strongly confirmed. Here I add that it's not only discoverability, optimality, but that's stated in the DLO, but it's a non-accidental regularity. So I have a step-by-step argument here for thinking now that we've got good reason to believe under the evidence of this optimality evidence that this is close to 1 is it's not small here. And the reason it's not small is because when we start off, okay, wait, this is not small. Under the DLO star, this would be expected, the fine-tuning, for the parameters to be in this discoverability optimality region. That's what E is. Under naturalism, which I take to deny this because it has a teleological component in it, and I think naturalists would not be very happy with that thesis. This is very, very much less than 1 if you put an equal probability distribution over the space. Therefore, by 1 and 2, the DLO is strongly confirmed over N. It has a very large Bayes factor. And then I claim that this is not much, much less than 1. It has a decent prior probability because it's already supported by what Einstein and others had noticed in the laws of nature. And voila, you use Bayes' theorem. And I see Richard Swinburne there. So, okay, using Bayes' theorem, it comes out to be near 1. And then I claim that it fits much better with theism than naturalism, and hence supports theism over naturalism. That's the basic argument. Now, let me say some of the benefits of this discoverability argument over the standard anthropic one. I think it adds to the case from anthropic fine-tuning, so I'm not dissing that argument at all. First of all, it's not subject to a multiverse or any observer selection explanation. Many cases straightforwardly avoid the McGrew-Westrup normalizability problem due to infinite ranges. Like the cases in particle physics, the anthropic ranges are finite. So you've got a straightforward, that whole problem just doesn't arise. It makes falsifiable, I put that in quotation marks, really disconfirmable predictions. It can be disconfirmed. In fact, around 7 times I thought I had done just that by making mistakes. It's not subject to the old evidence problem because you could have believed that the universe is not highly discoverable. You could not believe that it wasn't fine-tuned for existence observers. And maybe perhaps for some people, theologians especially, it tells us something about God's purposes and affirms the use of scientific reasoning. So here I address some quick potential objections, and I think I can end in time. So one objection is that if a domain were not discoverable, we would not know what we are missing. So it's sort of a selection effect. Well, with this optimality thesis, it avoids the selection effect objection. So as an example, here's the CMB. As I thought when I initially, in 2011, I thought we were somewhere down here. It wasn't optimal. And so we could have certainly been sad to find out that we weren't at the best point. Okay, so it cannot be explained by this discoverability selection effect. Some have raised what I call the tip of the iceberg objection. According to this objection, we only know of the tip of the iceberg of physical reality. Hence, we can make no claims about whether the iceberg as a whole, the universe, is fine-tuned for discovery. And anybody familiar with Bayes' theorem knows why that's not a very good objection. We make inferences all the time from limited samples. Bayes' theorem tells us that as long as the apparent discoverability of fundamental parameters in the sample are much more surprising under naturalism than the DLO or DLO star, they will strongly confirm the DLO star over naturalism. The only worry is if the tip was chosen because of, based on a discoverability effect, a selection effect, but as I showed before, that's not the case. And now, this was Carroll's objection. He thought this was, he could imagine many cases in which it would have been easier to discover the universe. And the problem is, he didn't distinguish between, in the case of the Higgs boson, detecting the Higgs boson. It could have, at lower mass, it would have been easier to detect. That's true enough. Same with the bottom quark, same with the top quark, charm quark. But they would have been far less useful tools for the ultimate goal of physicists is to probe the standard model. And so there would be really no ultimate discoverability advantage of being detected earlier. In fact, if they were detected too early, like the Higgs boson in the early 90s, they wouldn't even build probably the high energy accelerators that they need now to test whether in the TeV range there's a new physics occurs. So it's actually, there's another advantage of having it a little higher. But once you make that distinction, his objection vanishes. So that's the end of the main presentation. These are ways of, there's other slides here, but I ended 2 minutes early, so I can go to question and answers now. See, I fine-tuned that so it would end on time.
That's great. That's fantastic. It's another example of how you can definitely present a lot of great material in 30 minutes. Okay, so we have the roving mic for Q&A, and I will come around and give it to you, but I will still keep an eye on time so that we don't go over. If I can find my phone. Alex?
Okay, this is not a criticism. It's I'm wondering about a possible avenue for looking at this. Look, and whether you've done anything along those lines. So there's a bunch of stuff that's poorly discoverable, like We've got opaque bodies, hard to look inside them. Our cells are really small and we're really big in comparison to them. Our visual range is limited in wavelength. There's dark matter. A whole bunch of the universe is governed by nonlinear dynamics, and some particles in the standard model are hard to detect. So presumably the theory would be that in all of these cases, well, it's pretty crummy for discoverability, but it's the best we can do if we're going to have livability.
Not just that, it's also, I mean, you could imagine God just creating, like by fiat, a universe that, of a single galaxy, let's say, and upholding things, a very complicated set of laws, but then you wouldn't be able to discover the laws. So it's really, I say, interestingness, livability, and discoverability. That's why to keep to test discoverability, I hold those laws constant. Everything you're talking about is really because of the laws of nature.
I'm not sure. I mean, that's I think would be worth testing, is look at these things and see at the cases where things are not very discoverable and see, could those things be made more discoverable by varying parameters while keeping the laws constant?
Well,
and would you maintain livability?
Look at the finestructure constant. As an example, you could increase it, increasing the resolving power of light microscopes, which you wouldn't have with fires, and hence you be very much less likely would have had a scientific civilization to even have the light microscope. So by looking at these things across, moving them around, I have a limited range, a limited sort of worlds I look at. I'm holding the laws constant. And so that's how I avoid the objection, because if I start moving the laws around, changing the laws, it's sort of like all hell breaks loose. I don't know there's so many possible variations and there's so many possible effects that it's really hard to even get a handle on. That's why I'm taking a limited sample that's not biased for my thesis. It's a natural way of looking at, like you would do in a drug study. You take a limited sample so you can get a handle on what's happening with the drug.
So then you need for these cases an argument that to get more discoverability, the laws would have to be different. So for us to say have infrared vision, you would need the laws to be different or something like that.
Right. You need the laws to be different because, exactly, or you could try to move the constant around, but then you would have other problems would happen. Now, infrared vision, you're probably not going to be able to get, period, but infrared vision you might be able to have to think about that. But you have to change the laws. That's
so this is just a suggestion for future research.
Right.
Look at cases where there isn't much discoverability and see what's going on in those, because that might be what we want is we want to when we're testing a theory, right, try to find the cases that are likely to be hardest for the theory, right? So one thing we could do is we could look at random cases, and it's kind of some of the stuff you're doing in particle physics is that, and that is a good test for a theory.
Right.
But we can also try to fine-tune the cases we look at to be the cases that are likely, that our intuitions suggest are going to be the hardest for the theory. And at least my intuitions are that those cases are going to be cases where it's hard, where discoverability is poor.
Well, Carroll brought up quantum mechanics, but then I pointed out immediately, he said, well, classical world would be more discoverable. But a classical world wouldn't have worked. Atoms would have, the electrons would have come in on themselves. You don't have a workable classical model, a way of getting atoms, and so you wouldn't have life. And now general relativity might be a case, but there's another reason why a general relativistic world is actually better overall for discovery.
Rob Coons?
Great, Robin, this is great stuff. This is, I think, a fairly naive objection, so I'm sure you'll be able to come back. And I think it might relate to Alex. So I'm a little bit worried about the observability selection effect. Mm-hmm. So one might think, look, it's more likely that we would have already discovered those things which are most discoverable. And so it wouldn't be then so surprising when we check for the things we've actually discovered that they would end up being in the optimal discoverability range. It might relate actually to Alex's point, which is if we look at the things that were just barely observable or discoverable and see if those two lie in some optimal range, that would certainly help, I think.
Well, you would look at, I think the answer is the one I gave. I just elaborate on it because you can look at the range of this parameter where you would still know about it, like know about the CMB, and that's a fairly large range. And so why is it there'd be observers in this universe who would know about it, observers in another universe that would know about it? Why are we in the optimal range? Or like the tau lepton, if it was very much larger in mass, we would have known it existed. But we wouldn't have, it would have been pretty poor for the uses we want to put it to.
But yeah, but it seems to me that it might be more likely that we would sooner discover the things which are high in the optimality range.
But I don't think that is the case. I mean, I don't think well, maybe in the case of the CMB, it would be sooner to discover. I think that's the case there, but like the bottom quark was discovered before by a method, a resonance method. You have an energy resonance where these, the particle creation goes up, and that would have occurred whether it was in the optimality range or not. And it was only later they found, they were pleasantly surprised it was, had a long enough lifetime. So a few cases that might apply to it. I don't think it's going to do it across the board. It's going to work across the board.
Next question comes from Tim McGrew.
So, Robin, I love the fact that you're avoiding normalizability problems. That's very good. I do have a question arising from the way that you've laid this out. You've given us several different parameters, and we can think of them as forming a multidimensional space.
Right.
Our universe is located at the point of origin of those axes. You're exploring the axes one at a time. You're
Right.
moving up and down one while holding all else equal, probably just because of the computational unfeasibility of trying to covary. But I'm wondering if there's any way to get beyond that, because one objection that could be leveled, and to some extent you can anticipate this with the drug testing analogy, but still somebody could say, look, there's a ball in n space around the existing values, and you're probing such slender threads through that ball that there could be large regions of the space that are optimal or nearly optimal if you were to vary more than one parameter at a time. I don't think that's a crushing objection, but it would be lovely if there were any way even to get a grip on that.
In the particle physics cases, I do, because what I do is consider each particle in order. Like, to say, first start with the mass of the bottom quark, and then without any knowledge of anything else, and see, do the Bayesian calculation of the probability of it being in this region of the DLO and not DLO. Okay, then now we have knowledge, add the knowledge of the bottom quark mass, and now you conditionalize on that. So that's what I actually do in those cases, as I worked it out. It's successive Bayesian conditionalizations. This is what you have to do if you're going to combine them all together.
Right.
Okay, and that solves that problem.
Okay, that actually gets you out into the parameter space off the axes?
Well, that actually gives you the total degree of confirmation, which is what you're ultimately after.
I think I'm going to need to see the details on that.
Okay, well, yeah.
In some other slide, or maybe over lunch.
It is on,
Okay.
Yeah, I could.
Okay, we've got a question back there. I want to interject a quick question, Robin. Can you state real clearly what is it that the universe is finely tuned for in the data that you're considering here? The universe...
For our ability to discover its fundamental structure.
Right. So this is, I just want to make it clear, this is not the ordinary fine-tuning argument that says that the constants in the world are fine-tuned for it to be life-permitting, right?
Right, or observer-permitting, or,
Right.
however you do it.
So that raises a question of independence of
Right.
those data. Because if all of the data today are just downstream consequences of the data for the fine-tuning argument for the life-permittingness of the universe, then there's not going to be two fully separate arguments.
Right, in some of the cases, there's in some of the cases, it's very difficult to get a handle on whether the anthropic range might be narrower than we think it is, because like in the case of the CMB, so maybe the anthropic range is also pretty narrow around that peak. But even if it is, there's an independence in that case between the mathematics for calculating the anthropic range and the discoverability range. So then you get a coincidence of anthropic discoverability overlap. But that it's not as clean as I would like it to be. That's why the particle physics case, I loved them, because they're clean. When you vary the mass, let's say, of the charm quark or any of those parameters I talked about, as long as the Higgs field remains stable, they won't have an effect on livability of the universe, because these particles only exist for like a trillionth of a second or less. And they only occur in very, 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 very high energy processes as you get in accelerators. So they're gone before they can have any effect at all. So the only possibility there is an anthropic effect at the very, very early universes when the temperature was extraordinarily high. But other than that, there's that it doesn't just follow from their anthropic.
Right. So as I understand you, you admit the formal point that they could technically be dependent and therefore not have...
In the early universe case, but then I would just consider it a real coincidence that the anthropic and whatever it is it's suggesting, the very early universe happens to be such that the masses needed for that to lead to an anthropic universe are just right to also maximize discoverability on completely independent grounds.
Right. Good. So second really quick question. Sometimes, and this is a common sense sort of objection that people hear and may have in the audience, an objection to the fine-tuning argument for the life permittingness of the universe goes like this. Well, life could have been very different than it is, and what you have is an argument that the conditions for the universe are fine-tuned to permit carbon-based life of a certain level of complexity, but there could have been other forms of life, and so that changes the equation. Do you think there's a parallel objection here, that there just could have been other methods of observing the universe or discovering that parallel that earlier
Well,
objection?
I think you can do, in this case, put in the initial background information that, it's carbon-based life, it's humanoid kind of life, and because that could have been the background information of a 19th century physicist, right? And then that would be, and then if they knew this other stuff, they didn't know where the parameters were, they knew that somebody told them there is going to be these parameters, here's your possible variations that allow your kind of life, and here's the region in which they're highly discoverable, but we're not going to tell you where those parameters are. And they're a naturalist, they don't believe in any teleology. I think they'd be pretty skeptical. Pretty low probability you would assign it if you do an equal probability distribution that they're going to be in the place that leads to this optimal discoverability.
Right. There's, yeah. Brad Monton?
Robin, this is great stuff. I have many questions. So one question I have is, why would God... this is a really basic one. Let's go with that one. Why would God care about us being able to detect these obscure fundamental particles?
Yes, I mean, why, I've often... What's that? Oh, Pete. Yeah. I've often, that's a puzzle for me, exactly coming up with a good theological reason. One reason is, I think if, let's suppose God wanted to both strongly affirm faith of some sort and reason together, the paradigm of reason is science. And so to find that within science itself, what allows for science to occur is the fact that the universe is teleologically structured, that would be one of the best ways of doing that job. Now, there might be other reasons God would care, but I think that's one of them, and at least sufficient to not make it surprising that God would do that. Now, if you noticed also in the slides, I never much talked about God because I'm concerned initially with just confirming this DLO star thesis. Okay, and then we can, as a second order, we can say, well, does God make the most sense of this, or can you accommodate it within naturalism?
Perfect timing. Thank you, Robin. Let's thank him again for his fine presentation.